Welcome to this lecture. This lecture is on physical vapor deposition. If you remember, in the last lecture we were talking about silicon dioxide, and in silicon dioxide we are talking about a different way to grow silicon dioxide. One is your CVD, which is chemical vapor deposition, and second is your PVD, which is physical vapor deposition, right. In physical vapor deposition, that means you have a material which is in physical state and you have to melt it, or you have to take the, bombard the ions so that the atoms would be dislodged from the material, and there is a deposition of this film on the substrate. So, mechanical way or electrical way of depositing the film, which is physical in form, from the physical form to the thin layer, is called physical vapor deposition. This is just a very easy way of teaching you, but within the physical vapor deposition there are different techniques. One is called thermal evaporation, second is called electronic beam evaporation or e-beam evaporation, and the last one is called sputtering, right. So, let us see each one in detail. This lecture we call as a thin film deposition techniques and physical vapor deposition. So, physical vapor deposition now is more versatile than CVD. How you know how it is more versatile than CVD? Once we look at the CVD, which is the chemical vapor deposition, then we will see that how we call PVD as more versatile than CVD, and PVD allows us to deposit most of the materials that are used in fabrication. So, that is the advantage of PVD. If you have silicon wafer, and on silicon wafer you have your oxide, that means it becomes oxidized silicon wafer. Just for representation, I am not drawing the oxide on both the sides. If you want, you can draw it also. So, silicon dioxide on silicon wafer, you start with silicon wafer and then you have silicon dioxide, right, like this. Can you deposit silicon dioxide with PVD? Yes. Now, you have a wafer once again, which is oxidized silicon wafer, and you want to deposit, let us say, metal. Can you deposit a metal? Let us say you have aluminum. Can you deposit this metal with PVD? Yes. On this metal I want to deposit zinc oxide. Can I deposit zinc oxide with PVD? Yes. You see the versatility, that you can deposit insulator, you can deposit metal, you can deposit semiconductor, you can deposit semiconducting oxides on the silicon wafer with help of the PVD, and thus PVD helps us to or is a technique by which we can deposit almost all the materials that are used in the fabrication. So, let me just rub it around. Okay. So, now in the PVD, the surface reaction occurs very rapidly, and so very little rearrangements of atoms occur on the film surface. Now, first you should know how this thing works, right. So, let me do one thing, I will just get one more slide. What we are talking about in this case is that in PVD the surface reaction occurs rapidly. Okay. What is surface reaction, what is rapidly, and what do you mean by very little arrangements or rearrangements of the atoms, right. First, let us understand how the PVD works. So, you have a holder that holds the material, and in the holder you put the or you load the material, you load the material. Then you have a plate to hold the substrate, a plate to hold the substrate. So, this is called substrate holder, right. Substrate, what is a substrate? Silicon or oxidized silicon wafer, right. What is this? this would be your source. So, you can say source holder. Just to make it easier, we call this particular holder boat. Okay. We call it as a boat. This was easy. You have oxidized silicon wafer, you have a substrate holder, you have a source holder or a boat, right. Instead of boat, we can also have a coil in which you can load the wires like this. These wires are your, let us say we want to have aluminum as a source material. So, these wires are also aluminum, all right. The substrate holder and silicon wafer or oxidized silicon wafer remains as it is. Okay. Now, you apply a voltage. So, I will just remove, you will remember, right, the bottom is called, this one is called, so source is called boat, right, boat, and what material we have, aluminum. So, we apply a voltage right, very high volt to this particular boat or to this coil. Okay. What will happen? Depending on the resistance of this material, depending on the resistance of the coil, right, the current will flow through. When current passes through, there is I square R heating. I square R is called Joule heating, right, Joule heating. Now, because of the Joule heating, because of the I square R heating, the material loaded onto the boat will melt, right, this will get melt, and finally after melting it will start evaporating, it will start evaporating. In this direction, right. Same thing goes here also. Let me draw the substrate little bit bigger, right. What is this? This is your oxidized silicon wafer, and as I said, the material will start melting and evaporating, right, in this direction. Correct. But if there is air, so now let us use a logic. If air is what, insulator or it is a conductor? Air is an insulator. So, if I hold a power cable where there is lot of power, right, that passes or at the end of the cable, can the shock, let us whole example, so that is good that you can see me now. Suppose this is insulator, okay, I am wearing a proper gloves, I am holding it through some equipment, and at the end of this there is very high voltage, extremely high voltage. If I show it to you like this and you are standing, let us say 2 feet away from me, I am just showing you like this, would you get a shock? Most likely not, right. Why? Because there is a air in between, and air is an insulator. So, possibly when we are heating this material, if there is a air, then there is lot of collision with the particles in the air, right. That collision will call distraction, and because of that the material that is melted may not reach uniformly to the substrate. So, what is an alternative? Alternative is that we make sure that the material can travel as much as possible without colliding with any other particles. That means, the material that we want to deposit, when it is melted, when it is evaporated, can travel at the max distance before it collides with anything. If it does not collide, then we can get a better uniform material layer or thin film on the substrate. So, to do that, what is a solution? You have a vacuum. So, that entire thing is kept in a vacuum chamber. This entire thing is kept in a vacuum chamber. Okay. So, then there is a term that we will learn called mean free path. Mean free path. Okay. So, the mean free path will increase in presence of vacuum. Okay. This much is easy, right. So, now what we were learning here is that because this material, that is a source material, in this case we have taken aluminum as a material, right, aluminum. So, the source material, when it melts and evaporates, it evaporates so rapidly that the layer that forms here, right, let us say this is a thin layer, it forms so fast, this layers form so fast that very little time for rearrangement of the atoms occurs, right. This deposition occurs so fast that very little time is there for the atoms to rearrange itself. Okay. That is what we were learning. You see this one, very rapidly, so very little rearrangements of atoms occur on the film surface. As a result, the thickness uniformity, shadowing by surface topography and step coverage can be very important issues in PVD. What is step coverage? We will see. So, now if you see that you have a material, this is your silicon and then this is silicon dioxide in this pattern. Okay. Now, if you deposit the material, no, then material will get deposited here uniformly, aluminum will get deposited here also uniformly, aluminum. Okay. This is aluminum, this dark one, this is aluminum, this is aluminum, but in this step, this region, the deposition will not be so uniform. Okay. That is called step coverage, to cover the step uniformly, this area. This step will not be covered uniformly, right. That is what is called the thickness uniformity, shadowing by surface topography and step coverage, right. Step coverage is very important in lot of application, and that is why that is a limitation of this particular or the issue with the PVD, right. So, in this module let us understand three techniques. First one is thermal evaporation, second one is e-beam evaporation and third one is sputtering. Okay. So, now the question here is that if I say that I am going to deposit 1 micron aluminum, okay, I am going to deposit 1 micron aluminum, how would I know that it has reached 1 micron? That is my first question. Can you guess? I will just give you 10 seconds to guess and then we will get back. Think about, if I want to deposit 1 micron aluminum, how would you know it is 1 micron? Any idea? Even if you have, I cannot hear, is not it? That is a limitation of online, that interactions are less, and that is why we have portal, right, NPTEL portal. So, you can ask us questions, doubts through the NPTEL portal. Do not ask solution for the assignments, not allowed. So, what we will do, we will have, we can use the principle of piezoelectricity, piezoelectric. What is piezoelectric? When there is a pressure, there is change in the voltage, right. So, you remember what kind of materials are used for piezoelectricity, or what are materials that have piezoelectricity, right. If you recall, there is a material called quartz. So, quartz quartz crystal can be used to measure the thickness of this particular material. That means, I can place a quartz in this region. This is a quartz. So, the material that gets evaporated right onto the wafer, which is a substrate, will also get evaporated onto a crystal which is quartz, and when it gets deposited onto the quartz, there is a change in the voltage. So, we can use a quartz crystal monitor called QCM to monitor the thickness of the material that we are depositing onto the substrate. That is the first point that you need to remember, right. QCM, quartz crystal monitor, can be used to monitor the deposited film, how much film is deposited, rate of deposition. The another question is that when you heat this boat, when you heat the boat, right, the material is melted, but it will take some time for the material, all the material to get uniformly melted, right. So, should we start evaporation as soon as we apply the voltage to the boat, or we wait for certain time? So, initially you have here a plate which will cover or mask the deposition, right, and once these things are uniformly melted, right, this plate is opened. So, it goes in a different direction, and then you can deposit your material, you understand. So, you wait till the metal gets melted and then you open the masking plate, right. So, that when you start deposition, it will be uniformly deposited, and you can always close the deposition not by just dropping the voltage, but by bringing the plate back into this direction. So, if you bring the plate back, right, the material that gets deposited will not reach in this region, correct. So, that is how the things are done. So, let us see the slide. You can tell me what is this material, this system and this system. Can anybody guess? See what are the things in the system. See very closely and carefully, and then we will continue discussion. Just I will give you 1 second or 2-3 seconds to look into the photographs. Okay. Okay, you are able to see. Now, let us start with the number 3. This is number 2, this is number 1. So, this is thermal evaporation system, okay, and this is electron beam evaporation system. This is automated thermal evaporation system. This is manual thermal evaporation system. Right, evaporator, thermal evaporator, and this one, right, is a knob to apply the voltage. This is the meter for understanding how much current flows through the source holder or a boat. These are the windows to see, you can see whether the boat is melted or not, or whether, sorry, the source in the boat is melted or not. If boat gets melted, what will happen? All the things will fall, and that is the reason why in mistake also I said that if the boat is melted, what will happen. So, when the boat gets melted, let us say you have this and you have material here, and you apply voltage, and the current becomes so high that the boat itself starts melting, the material of the boat starts melting. What will happen? This is not a good idea, because then you have two different metals, right, getting deposited onto the substrate, forming an alloy, right. So, always understand that the material that is used for boat, should have a way higher melting point compared to the material that we use for deposition, alright. So, here the material that we use for deposition was aluminum, the material that we use for boat should have way higher melting point compared to aluminum, right. That is a very important point. And for the material which will have the melting point similar to boat material or way greater than boat material, then thermal evaporation fails. Okay. We cannot use thermal evaporation where the material that we are depositing, its melting point is way higher than the melting point of the boat material. Okay. So, you need to be careful on where to use thermal evaporator and where not to use thermal evaporator. Now, what other things you can see? Okay. That is not all about thermal evaporation. The other thing that you see is this one. This is a chamber. So is this one, and so is this one. These are all chambers. Now, you say, oh, you drawn like this, but this does not look like this. It does not have to look like this. Okay. What I am saying is there should be a chamber in which you can create a vacuum, right. And in this case you have two windows, actually you see here closely, but this is very clearly you can is visible. One is the window to look at the substrate, one is the window to look at the source, one is a window for the substrate, one is a window for the source. Okay. Easy. What we have seen? There is a, and of course, here whole electronics is there to apply the voltage. Here it is automated, you set the parameter, automatically deposition will occur and it will stop. Now, the other things very important to understand the equipment, so that it becomes easier, and just we are not just doing this for the sake of theory. Okay. I will be showing you the experimental labs in which we will show how the e-beam and thermal evaporation system actually works. Okay. So, let us not worry about it too much if you do not get too much clarity from this schematic or from the photographs. Okay. The next thing that we need to see, if you see the picture, is this particular region. In this it is not too visible. In here everything is within it or on the back side of it, but this is a good photo, because I want you to look at this particular gauge. Okay. There are generally two gauges. So, this is, by the way, secondary pump, and then always there is a primary pump. Okay. Primary pump and secondary pumps are used to create vacuum. Okay. And generally we use turbomolecular pumps to create vacuum. Vacuum can be 10 to the power 6 to 10 to the power 7 torr, right, 10 to the power minus 6 to 10 to the power minus 7 torr. This will be a range in which the vacuum is created into the vacuum chamber, right. And because every or physical vapor deposition method, whether it is thermal evaporation, whether it is e-beam evaporation, or whether it is sputtering, right, all the three different techniques or evaporation techniques are or requires, right, all three evaporation technique requires vacuum, and that is why these techniques are also called vacuum deposition techniques. So, if in some books if you see vacuum deposition techniques, do not worry about it, right. Physical evaporation techniques are also called vacuum deposition techniques, okay, because the deposition occurs in the presence of vacuum. Okay. So, now what you have seen, primary pump, secondary pump, these pumps are used to create vacuum. Now, let us go to the next point. It is very complicated than what I am showing it to you. Okay. I am just showing the easy part of this system, right. The system is way too complicated, but we do not have to worry, because you have to utilize the system, not make the system. If you are interested in making an entire system with electronics, then we can go into that particular direction. Right now you should be interested in what kind of systems are there and how we can use the system. Okay. So, now there is one more thing here, this is called gauge. Okay. There are two gauges, one is called Pirani and Penning, Pirani and Penning gauges. Okay. So, the Pirani gauge is used for measuring low vacuum, about 10 to the minus 3 torrs, and greater than 10 to the power minus 3 all the way to 10 to the power minus 7 or minus 8 torr can be measured with the help of Penning gauge, right. Pirani is still 10 to the power minus 3, Penning is for greater than 10 to the power minus 3 onwards. So, these are some of the things that you need to understand about the evaporation system, right. Now, as I mentioned, we can divide the physical vapor deposition into two techniques, one is evaporation, one is sputtering, but within evaporation you have thermal and you have e-beam, okay, thermal and e-beam. Now, we also discussed that there are three deposition techniques, and that is why I said 3, okay. But based on the way the film is deposited, thermal and e-beam falls in similar zone, while sputtering falls in another zone. Okay. So, physical methods produced the atoms that deposit on the substrate, we can call them as the evaporation or sputtering techniques, and sometimes called vacuum deposition, right, because the process is usually done in a evacuated chamber. Now, generally PVD is used for depositing metals, but dielectrics can also be deposited using specialized equipment. So, let us go to the next slide. So, in the evaporation techniques of PVD, a vacuum chamber is pumped down less than 10 to the power minus 5 torr. Okay. That is the first thing we need to understand. Second is that evaporation atoms from the source condense on the surface of the wafer, right. We have seen that when you melt the material, it will get deposited onto the wafer. The rearrangement of atoms will not happen or does not have that much, we do not have that much time, because the deposition occurs so rapidly, right. So, atoms would not have time to rearrange itself. The heater can be of resistive type, generally tungsten filament is used and it heats up as the current flows through it. Now, this depends on again what kind of material that you use, whether it is resistive heating or some other types of heating, but the most popular is an e-beam evaporation system, in which a high energy electron beam is focused onto source material in the crucible using magnetic fields. So, when the E beam comes, I will tell you what is advantage of E beam. Right now just understand that E beam is you have a crucible, alright, and there is a electron beam that is created. It comes and it scans this particular material, and because the heat that is created because of the electron bombardment, right, onto this material, right, this material gets melted and gets deposited. But the way to travel and to form an angle, right, all these things are not so easy. We need to understand how the magnetic fields, where the magnets are placed, how the accelerator works, how the electrons are accelerated further, right, how the bending works because of the magnetic field. All these things are important. You have a spot beam, you have a raster mechanism for the beam. So there are different way of using electron beam evaporation system. Why to use E beam is very simple reason, that you have substrate source either like this or this, right, and if the material that we use on this one, right, like this material M, if the melting point of material is way greater than melting point of boat or source holder, thermal evaporation fails, right, because this material will evaporate faster than the material that we want to deposit. So that is why when these are the cases, when such materials we want to deposit, we go for the electron beam evaporation. Okay. And that is the reason of E beam evaporation. When the material that you want to deposit has a very high melting point, then the material that you are using for the boat, then we need to go for E beam evaporation system. And depending on the method of evaporation and the hardware, evaporation technique can be categorized as thermal evaporation and E beam evaporation. Now very important thing that comes when we are depositing a film using this evaporation technique, and that is called mean free path. Here mean free path is given by lambda, and mean free path lambda is nothing but the average distance a molecule travels before it collides. So you have this boat and you have this substrate here, how much the material that is here, how much material can travel before it collides with something and gets distracted, right, how much it can travel. So the higher the mean free path, the better the chance of we have deposition, uniform deposition, right. So this with what it will collide? It will collide with some particles or residual gas molecules, and to remove these residual gas molecules we use vacuum, right, to increase the mean free path. The longer the path is, the better the deposition, correct. So the mean free path lambda is average distance of a molecule travels before it collides with the residual gas molecule, and it is given by lambda equals to kT by under root of 2 pi Pd square, where T is absolute temperature of the chamber, D is gas molecule diameter, pressure is P, K is Boltzmann constant. And if you want to take an example, right, to solve it, right, we will solve a lot of mathematical questions, some problems in the TA class, but let us take one such example here. Consider a nitrogen gas molecule whose diameter is 3 angstrom and the temperature of the chamber is 300 Kelvin. Calculate the mean free path of the gas. Now if you have 3 angstrom, which is D, T equals to 300 Kelvin, we know the formula lambda equals to kT by under root of 2 pi Pd square, and we put the values, right, then we can say that for 10 raised to power minus 6 lambda would be 78 meters. The gas molecule can travel for 78 meters without any collision with other molecule if your P equals to 10 power minus 6, and if the gas molecule diameter is of 3 angstrom and if the temperature of the chamber is 300 Kelvin, right. So, this is way the lambda is calculated. Like I said, higher the mean free path, better the chances of uniform deposition. The next question that comes into our mind is the what are the different kind of evaporation sources, right. Now, I have shown it to you in the drawing in the schematic, but these are way more than what I have shown it to you, correct. These are all evaporation sources, okay, all evaporation sources. And you start with the tungsten wire sources, right, tungsten wire sources. So, tungsten is used as a crucible material. This evaporant wets tungsten and retained by surface tension. The refractory metal sheet sources are made up of tungsten, tantalum and molybdenum sheet materials and is used for poor wetting evaporation, evaporants or powders. Then we have sublimation furnaces in which the evaporation of sulfides, selenides and some oxides as pellets are possible. The evaporation from these sources tend to be constant over extended periods of time, while there are crucible sources, generally cylindrical cups of Al2O3, Bn, graphite and refractory metals that are used as a crucible sources and normally heated by external tungsten wire, and sometimes high frequency induction rather than resistance heating is also used for such sources. So, if you see the thermal evaporation, then like I have shown it to you earlier, there is a vacuum chamber, then there is a wafer holder, you can say substrate holder, and then there are wafers placed here, right, source material or heater resistance here, there is a vacuum system, right, that will help to keep the vacuum intact, and then the thermal evaporation systems relies on energy supply to the crucible, which is crucible is here, right, or boat to evaporate the atoms. Evaporated atoms travel through the evacuated space between source and the sample. Surface reaction usually occurs very rapidly and there is very little time of rearrangement. You see, this is again we came back to the same point that there is very little time of rearrangement of the surface atoms after sticking. The thickness uniformity and shadowing by surface topography as well as step coverages are the issue. So, in this case if you see, these are the substrate, these are the source holder, 4 source holders are there. This is the photo within the thermal evaporation system and we can have 4 different sources. At a one time only one source can be used, but we can load different material and we can also form different layers of the material or the alloys. Okay. So, we will go to the next slide, and next slide is a video. So, I will just play the video, you look into the video and see how the thermal evaporation works. Okay. Then the question that comes to our mind is what happens if we want to evaporate an alloy. So, in that case the binding energy of metals in alloy is different than the binding energy of atoms in metal, that we already know, correct. So, the metal atoms are less tightly bound than atoms in an inorganic compound. Constituents tend to evaporate independently depending on temperature and enter vapor phase as independent atoms. Thus, let us take an example, let us say A and B are 2 metals and AB is an alloy, okay. It is a mixture of 2 metals. I hope that you know what is alloy, okay. Now, activation energy of AB bond is different than activation energy of AA or BB bonds, you agree with that. So, metallic melts can be considered as solution of 2 materials. Partial pressure of A in AB at temperature T, PA is not equal to partial pressure of pure A at T or PA at 0. Similarly, B for material B, the partial pressure of B in AB is different than from pure B, right. So, PA can be gamma A, X A, rho A or PA 0, where the gamma A is the activity coefficient and X A is a mole fraction of A. So, from this what we can understand, actually to cut the story short, we can find out the flux ratio, okay. And from flux ratio we can understand how the materials that are we are using for forming an alloy, right, has to be considered, and how the vapor pressure as well as film composition depends on temperature and properties of the materials. Alright. So, when you want to deposit an alloy, you need to understand that what should be the temperature, what should be the property of material, what should be the vapor pressure. Now, what we have discussed earlier is on the thermal evaporation, and I told you the limitation of the thermal evaporation system, that in thermal evaporation system, if the metal or the material that is loaded onto the source, its melting point is higher than the source material, we cannot use thermal evaporation, but in that case we can use the e-beam evaporation. And you can see this particular schematic, you have a filament, right, where there is a generation of the electrons, then there are accelerator electrodes to accelerate the electron beam, right, then there is a electron beam which is forming here, there is a deflecting magnet which looks like this, and then this deflecting magnet will deflect the electron, and the electron will be focused, or the beam will be focused on the crucible that contains the source. When electron beam either as a point source or as a raster scanning falls on the source which is loaded into the crucible, the material which is the source material will start melting, and this molten material will start evaporating. Thus, in this case you are not heating the crucible, correct. That means the crucible has to play, the material of the crucible has to play no role, except that it should withstand high temperature, and there is a coolant also on the back side to keep cooling the crucible from the back side. Alright. Now, if you see the second schematic which is here, right, you can see how you can block the evaporation, still you feel that there is a uniformity of the melting material. Here also you can see the same thing, right. This is the material here, when it starts evaporating you can remove this thing from the evaporation site, and then you can deposit the material. Okay. So, but this very important plate, it is a masking plate that will not allow the material to get deposited, because the substrate is somewhere here. If I just have a bigger chamber, right, and here the material gets deposited, but it cannot pass through this, right. Only when you remove this plate from the path, then only the material will start depositing onto the substrate. So, electron beam or e-beam evaporation is a physical evaporation technique that allows the user to evaporate materials that are difficult or sometimes even impossible to process using the resistive thermal evaporation. Some of these materials would have extremely high temperature. Now, for generating the electron beam, an electrical current is applied to a filament which is subject to high electric field, it is here. This will causes the electrons in the filament to escape and accelerate with the help of accelerating electrodes. The electrons are focused by magnets to form a beam directed towards the crucible that contains the material here. The energy of the e-beam is transferred to the material to start evaporation, and many materials with either melt or sublimate, directly sublimate. So, this is a region where you can have your crucible, the electrical supply, electron filament gun, wafer cooling, and deposition monitor, right. You can see quartz crystal monitor, deposition monitor. So, generally the QCMs are present within the chamber so as to measure the deposition rate. So, as we have discussed earlier, the e-beam evaporation is a rescue for the users who would like to use materials which have extremely high melting point. The water cooled crucibles, or in the depression of water cooled copper hearth, the source holder is placed, which is crucible is placed, and in the crucible there is a source. The electrons are ionically emitted from the heater filaments, but are shielded from direct line of sight of the evaporant charge and the substrate. The filament cathode assembly potential is biased negatively, of course, with respect to the nearby grounded anode, and this will accelerate the electrons. A transverse magnetic field is applied which serves to deflect the electron beam in a 270-degree circular arc, and then the focus it on the earth and evaporation charge at the ground potential, right. So, let us see the video for the same and we will continue from there. So, what are the power densities, right? Practically the power densities are approximately of 10 kilowatt per centimeter square and are utilized in melting metals, but dielectric require only 1 to 2 kilowatt per centimeter square. The contamination level of the deposited film using e-beam evaporation is less compared to other EPVD methods. The e-beam current density J leaving the hot filament is due to the thermoionic emission that we know, and is expressed by Richardson's equation, which is given here, and near to the evaporation surface evaporant flux shows a laminar flow, while the uniformity of the thickness can be described by the cosine law, right. Now, you please read why we are placing the substrate at almost 90-degree with respect to the source material. It was a reason, right. Just look into that and then you understand what is cosine law and you will have your answer. So, when you talk about e-beam evaporation, then there are e-beam evaporation sources as well. So, there is a single source where you can only hold one material, then there are rotary pockets, that means you can have 4 different rotary pockets. If the first is exposed, then you can rotate it, then the second will expose, then you can rotate it, third will get and fourth will get, like this is the rotary mechanism. You can also have linear pockets where you have multiple sources, but linearly it comes in the path of the electron beam. So, let us read the first one, which is the single pocket. A water cooled copper block is bored out to us have a pocket in the shape of inverted truncated cone. Source material is placed here, so is placed inside, okay. And within a crucible or whose exterior fits squarely within the pocket. So, when you have this, when I am drawing this, it is not exact, but the point is it will just fit very well in this region, okay. It will not come out, will not go too deep, exactly it fits well here. So, that is a source holder that fits well, or crucible. A magnetic structure consists of a permanent magnet and 2 pole extensors are located around the block such that field lines run parallel to side of the block. On the same side of the block is a filament, right. This is same thing that they are saying, but the point is it comes from here and the beam is focused here. So, electron beam energy is controlled such that the magnetic field will bend it precisely into the center of the pocket as I have drawn in the figure, right. An additional electromagnetic coil called a sweep coil is employed to effectively raster the beam. So, one is that continuously the beam falls on this source and then this is a point. So, the deposition is faster. Second one is it will go like this, then from here, then here, then here, then here again like this, okay. And this way. So, triangular formation, raster formation, all things are possible because of the electromagnetic coil which is additional called as a sweep coil is placed in the mechanism. A variety of patterns are used in control program for electromagnetic coil. Materials with lower melting points melt readily and fill the crucible. They do not require XY sweep, but the materials with high melting point, you see this is a very important point, requires the XY sweep to prevent the electron beam from boring a hole, because if you just keep on using this electron beam at one particular source, right, let us say this is the material, right, it will start only taking out the material in this fashion, right, for the materials that are of high melting point. This is a material, and if your electron beam is only focused on one point, it will form a hole, okay, form a hole, and that is what we do not want. So, in that case you use the XY sweep. As I mentioned, a rotary pocket electron beam source has all same paths as single point unit. However, with the design, a number of different materials can be evaporated sequentially, because like I said, this is if you say this one is the first pocket, right, and you have 4 pockets, then you can have different sources that you can evaporate. This design includes additional shielding to prevent cross contamination. This is this shielding, this one, okay. This is a shielding, and the pocket in position is chosen via motorized or rotary indexer. The final one, which is a linear pocket electron beam source, is similar to rotary pocket source, except that its pocket are arranged in a line and are indexed in a position in a linear fashion with a common magnet emitter sweep coil structure. All right. So, these are 3 different type of electron beam evaporation sources that we need to kind of just understand, right, that there are 3 different evaporation sources. What for electron beam evaporation. So, here we will stop, and the next class we will continue what is glow discharge and plasma, and followed by PVD sputtering techniques. In fact, let us do this thing. Let us finish the glow discharge and plasma, and we continue DC sputtering in sputtering in the next class. Okay. So, let me continue. So, the glow discharge and plasma, what exactly this means. Okay. So, now you have, but actually this glow discharge and plasma comes into play when we go for this sputtering. So, let us understand first glow discharge and plasma, and then we go further into the mechanism. Okay. So, here you have again a chamber, you have a matching network. So, we have moved from the e-beam and thermal evaporation to a technique called sputtering, where it is a mechanical way of dislodging the atoms from the source and depositing onto a substrate. Okay. First, let us understand what exactly glow discharge and plasma is, and then we will see how the sputtering works. So, in this case again we require vacuum, because sputtering is also a vacuum deposition technique. Okay. It requires vacuum. Then we have either DC sputtering, or we have RF sputtering, radio frequency sputtering. So, these 2 images that you see, right, are of both DC and RF sputtering, and in RF sputtering you require a matching network as well. The 13.56 megahertz is the RF frequency. Then you have a target, you have a substrate. So, you see here the substrate are placed and are in this fashion, right. Until now what we are doing, the substrate source was at the bottom and the substrate were at the top. In this case, the substrate is at the bottom and the source is at the top, right, source is at the top. So, this is the source. So, these are the plates, okay. These are the plates, and the substrate are anode, source is cathode. We can apply the sputtering gas, we can flow through here. Generally argon is used as a sputtering gas, and from the cathode to anode there is a cathode sheet, there is an anode sheet, right, and when you apply a potential, this is how the difference between anode and cathode can be seen. And also very important point is that the positive ions in the discharge glow strike the target and eject neutral atoms by momentum transfer, and the electrical neutral plasma contains partially ionized gas composed of ions, electrons and neutral spaces. The secondary electrons, dissolved gases, X-rays and photons can be emitted from the target. Now, what exactly all these things that I have read means. Okay. So, first thing to understand is that between the cathode and anode, so between this one and this one, or this one and this one, right, we apply some kilovolts of power densities. Okay. So, kilovolts of power. The substrate may be grounded, electrically floating or heated or cooled. After evacuation of the chamber, a gas, typically argon, as I told, argon is used as a sputtering gas, right, for this sputter, is introduced to serve as discharge medium, and a sustained visible discharge called avalanche breakdown of the medium is maintained between electrodes, and a film condenses on the substrate, which is anode. Now, what will happen is, because of this voltage that we apply between cathode and anode, the positive ions in the discharge glow strike the target. So, in the glow discharge, this will strike the target. Let me just when you introduce the sputtering gas, right, the positive ions will start striking the target from the glow discharge, striking the target. So when it happens, what will occur? The neutral target atoms will start dislodging, and when we start dislodging, what will happen? It will form the layers on the substrate, right. That is what it means. Discharge glow strike the target, eject neutral target by momentum transfer, and this pass through the discharge region to deposit the film on the substrate. Again, when you have vacuum and you allow the argon to flow, and you apply a very high voltage, there is a glow discharge, the argon ions will bombard the target, and the atoms from the target, the neutral atoms from the target, they are dislodged and they form a thin film on the substrate, right, and substrate are silicon wafer. The next thing is the electrically neutral plasma contains partially ionized gas composed of ions, electrons and neutral species within, and also very important is when there is this striking of these ions onto the target material, right, the secondary electrons that are dissolved gases and X-rays and photons can be emitted from the target. So, this is something, it is very important, and that is why sometimes the sputtering is not used for fabrication of some of the electronic materials, electronic devices like transistors, because the secondary electrons in the X-ray would cause the damage while fabrication. But for us to just understand, focus on that when the ions are bombarding on the target, there is a secondary electrons, then there are X-rays and photons that can be emitted from the target. So, if you want to understand further that how the glow discharge and plasma between the cathode and anode occurs, then you need to understand that when you apply a voltage between cathode and anode, the next to cathode is always a cathode glow and the next to anode is anode glow. So, first is there is a cathode glow, one is a anode glow. Okay. Then the substrate are placed here and you have a negative glow, and then there is something called cathode crux or dark space. Okay. The crux dark space and or cathode dark space, and then between the positive column and the anode here there is something called Faraday's dark space. Okay. And between anode glow and positive column there is a anode dark space. This much you understand. Now, the DC glow discharges consist of few luminous regions. Adjacent to the cathode there is a highly luminous layer known as cathode glow, where neutralization of the incoming discharges ions and positive cathode ions occurs. Second electrons start to accelerate away from the cathode in this area. In between the crux dark space, a region where nearly all the applied voltage is dropped. Within the dark space, the positive gas ions are accelerated towards the cathode, right. So, the positive ions are accelerated towards the cathode, and what happens is that the next distinct region is negative glow, right, where the accelerated electrons acquire enough energy to impact ionize the neutral gas molecules. Now, beyond the Faraday dark space, which is this one, right, and finally the positive column, the substrate anode is placed inside the negative glow during the discharge or during the sputtering, and the breakdown voltage that is required for creating the plasma is given by the Pascal's law, which is right over here, where P is a chamber pressure and L is the electrode spacing and B is constant. So, it is very important to again understand that what should be the distance between the electrodes, that is between the anode and cathode. If the distance is more, then the deposition will be slower. If the distance is too close, the heating of the substrate will occur. So, that is why sometimes you have to cool down the substrate, and also the pressure is very important in case of the sputtering. So, this is some of the things that we need to remember when it comes to glow discharge and plasma. In the next lecture, right, we will continue with sputtering and the types of sputtering. Just you need to understand glow and plasma discharge. Again, I will not be asking you questions from that, because it is just understanding about how when you use sputtering what is within the chamber. Okay. So, let us not go into thin film physics, but let us understand that there is a glow there is a plasma discharge, and then there is a voltage between anode and cathode, right. What are the mechanism when you apply argon or when you insert the argon gas, how the ions bombard the target, dislodging the atoms. So, dislodging the atoms, that means now you are not evaporating, you are not melting it, right, you are dislodging it. That means this is a mechanical way of depositing the film onto a substrate rather than melting the material and then evaporating. Okay. So, this is something that we need to understand. In the next lecture, we will be talking quickly on DC sputtering, RF sputtering, magnetron sputtering and reactive sputtering. Till then you just go through this class once again, right. Do not get overwhelmed with some of the terms, but just do understand that when we go for physical vapor deposition techniques, there are three. One is evaporation, one is sputtering. Within evaporation there is thermal evaporation and e-beam evaporation. And in sputtering there are different kind of sputtering where you apply DC, then DC sputtering, RF, then RF sputtering, magnetron sputtering and so on and so forth. And this all things falls under physical vapor deposition to deposit different materials. There is advantage and limitations of each of these techniques. So, we should be careful when you want to make a device, when you make a transistor, when you make a chip, right, which particular technique we need to use, right, and what are the advantages over the other techniques. So, till then you take care. I will see you in the next class. Cheers.